Okay, and welcome back. This week we're going to do chapter 4 on magma, igneous rocks, and intrusive activity. This is chapter 4. Let's look at the general characteristics of magma. Igneous rocks form as molten rocks cools and solidifies. Remember, igneous rocks comes from magma and lava. The general characteristics of magma include parent material of igneous rocks. They form from partial melting of rocks, and magma at the surface is called lava. Rocks formed from lava are extrusive or volcanic rocks. However, rocks formed from magma inside the earth at a depth are called intrusive or plutonic rocks. The nature of magma consists of three components. The liquid portion is melt. Any solids are silicate minerals. Volatiles are dissolved gases in the melt, including water vapor, carbon dioxide, and sulfuric dioxide. The crystallization of magma occurs in the systematic arrangement of ions into orderly patterns. Silicate minerals result from crystallization in a predictable order, and the texture is the size and the arrangement of the mineral grains. Texture is the overall appearance of a rock based on the size, shape, and arrangement of the interlocking minerals. There are numerous factors that affect the crystal size. These include rate of cooling. If you have a slow rate of cooling, you'll have fewer but larger crystals. If you have a fast rate of cooling, you'll have many small crystals. If you have an extremely fast rate, you'll form glass. The way you form an extremely fast rate of cooling is to have an explosion out of a volcano, and the magma cools very quickly in the upper atmosphere as it gets thrown up several miles. Factors affecting the crystal size include percentage of silica, SiO2, present, and dissolved gases. Now we're going to talk about a number of different terms of types of textures and igneous rocks here. So these words will look unfamiliar to many of you. I'll try to go through the pronunciation of them carefully. The first is phaneritic, or fine-grained texture. This is a rapid rate of cooling with microscopic crystals, and they may contain vesicles, which are holes from gas bubbles. Phaneritic is coarse-grained texture. This includes slow cooling and large visible crystals. So on the left you see a granitic felsic rock, granite. On the right you see a mafic rock, basaltic, out of lava, called gabbro. These are all types of phaneritic, coarse-grained rocks. Types of igneous textures. We have porphyritic texture. These are minerals that form at different temperatures. Large crystals, phenocrysts, are embedded in a matrix of smaller crystals called ground mass. A glassy texture is a very rapid cooling of lava, and the rock resulting is called obsidian, and we will look at this here in a minute. Pyroclastic texture is a fragmental appearance produced by a violent volcanic eruption, often appearing more similar to sedimentary rocks. Pegmatitic texture is exceptionally coarse-grained, formed in late stages of crystallization and granitic magmas. And we'll look at this. An example of a pegmatitic rock. See the coarse grain there? Here's one of my favorite types, obsidian. It's a very glassy texture, very smooth to the touch, shiny. Igneous compositions are composed primarily of silicate minerals. If they are dark in color or ferromagnesian silicates, they contain olivine, pyroxene, amphibole, and biotite mica. If they are light or non-ferromagnesian silicates, then they are formed of quartz, muscovite mica, and feldspars. The difference between granitic versus basaltic compositions is that a granitic composition is light-colored silicates, termed felsic because they're made out of feldspar and silica in composition, high silica content, silicon and oxygen, and a major constituent of continental crust. Basaltic compositions are dark silicates and calcium-rich feldspar. They are termed mafic, magnesium and ferrum for iron in composition. They have a higher density than granitic rocks and comprise the ocean floor and many volcanic islands. Other compositional groups include intermediate or andesitic composition. These contain 25% or more dark silicate minerals, and they are associated with explosive volcanic activity. Ultramafic composition is a rare composition that is high in magnesium and iron and is composed entirely of ferromagnesian silicates. Silica content as an indicator of composition are including rocks out of the crust that exhibit a considerable range of 45 to 70% of silica. Silica content influences magma behavior. Granitic magmas have high silica content. Basaltic magmas have a much lower silica content and are more fluid-like behavior. How do we name igneous rocks? Let's start with granite. Phaneritic, over 25% quartz, about 65% or more feldspar. Very abundant, often associated with mountain building. The term granite includes a wide range of mineral compositions. Rhyolite is an extrusive equivalent of granite, may contain glass fragments and vesicles. Phaneritic texture, and less common and less voluminous than granite. Obsidian, another favorite of mine, is very dark colored and glassy textured. Pumice is volcanic, has glassy texture, and a frothy appearance with numerous voids from air bubbles. Andesite is volcanic in origin and an amphinetic texture. Diorite is coarse-grained and plutonic equivalent of andesite. Basalt is in volcanic origin, amphiretic texture, composed mainly of pyroxene and calcium-rich paleoglazed feldspar, and is most common extrusive igneous rock. Basalt rock is volcanic rock. Gabbro is an intrusive equivalent of basalt. Phaneritic texture consisting of pyroxene and calcium-rich paleoglass. Significant percentage of the oceanic crust is gabbro. You can see this chart in your book. It's too busy to go through on the video, but you can see the different types of granitic to ultramafic rocks that we have, the dominant minerals included, and what kind of grain they have. This is also in your book. These are common igneous rocks. Again, you can see the different types and the different cooling rates you have. Naming igneous rocks, pyroclastic rocks composed of fragments ejected during a volcanic eruption. There are varieties of them. One is called tuff, which is ash-sized fragments. Volcanic breccia, particles larger than ash. Generating magma from solid rock. How do we reverse this process? The role of heat plays a part. Temperature increases in the upper crust, the geothermal gradient, an average of 20 to 30 Celsius degrees per kilometer. Rocks in the lower crust and upper mantle are near their melting points, and additional heat may induce melting. Here we can see a chart also in your book of a typical geothermal gradient, how the temperature increases as you go deeper into the earth. Pressure also plays a role. It increases in confining pressure, increases the rock melting temperature. When confining pressures drop, decompression melting occurs. Volatiles play a part, and volatiles are primarily water, causing melting at lower temperatures. An important factor where oceanic lithosphere descends into the mantle. So here we see that lithosphere descending into the mantle, and you can see the decompression melting going on with the magma going up through cracks in the surface to have decompression melting in the crust. One single volcano may extrude lavas exhibiting very different compositions. We have this example called Bowen's reaction series. Minerals crystallize in a systematic fashion based on their melting points. During crystallization, the composition of the liquid portion of the magma continually changes. So here's this chart, also in your book again. We'll go over it just real quickly here. The Bowen reaction series. As you go from a high temperature to a low temperature, you would start with a certain type of mineral and igneous type of rock. And as you go down into the various temperature ranges and cooling rates, you would get different types of rock forming out of this. Now, what can make a magma change composition? Magmatic differentiation is a separation of a melt from an earlier formed crystal, and assimilation is a changing of a magma's composition by incorporating surrounding rock bodies into a magma. Magma mixing is two chemically distinct magmas that may produce a composition quite different from either original magma. This chart is also in your book, and we can take a look at that later. Partial melting and magma formation. Incomplete melting of rocks is known as partial melting. The formation of basaltic magmas most originate from partial melting of mantle rocks at oceanic ridges, and the large outpourings of basaltic magma are common at the Earth's surface. Partial melting, formation of andesitic magmas, are produced by interaction of basaltic magmas and more silica-rich rocks in the crust. They may also evolve by magmatic differentiation. The formation of granitic magmas are most likely formed at the end product of crystallization of andesitic magma. Granitic magmas are more viscous than other magmas and tend to lose their mobility before reaching the surface, and they produce large plutonic structures. Most magma is in place at depth in the earth. An underground igneous body, once cooled and solidified, is called a pluton. They have various shapes, including tabular, which is a sheet-like shape, and they are massive. A discolorate pluton cuts across sedimentary rock units, and a concordant pluton is parallel to the sedimentary rock units. The different types of intrusive igneous features are including a dike, a tabular discordant pluton, a sill, a tabular concordant pluton, examples of the Palisades sill in New York. Laccolith is similar to a sill, lens or mushroom-shaped mass, and arches overlying strata upward. Here we can see at depth the plutons. Here's a sill in the Salt River Canyon of Arizona. Intrusive igneous features include a batholith, the largest intrusive body, surface exposure of 100 square kilometers, frequently formed in the cores of mountains. Magma at depth is much less dense than the surrounding rock. Increased temperature and pressure causes solid rock to deform plastically. The more buoyant magma pushes aside the host rock and forcibly rises in the earth as it deforms the plastic host rock. At more shallow depths, the host rock is cooler and exhibits brittle deformation. The movement of magma here is accomplished by fractures in the host rock and a feature called stopping. Melting and assimilation of the host rock is greatly limited by the availability of thermal energy. That's the end of chapter 4. It took about 14 minutes. Be sure to rewind the tape if you get any confusion and you want to go over another topic again. And be sure to send me questions if you have any. Thanks for watching.